Okay, so let us have this problem right here. So design a simply supported interior concrete beam 6 meters long having loads as follows. So we would be having a superimposed dead load of 10 kilonewtons per meter and an unfactored live load of 8 kilonewtons per meter. So according to the architect, the section is limited to a beam width of 300 mm. So basically, this is now our B sub W. And here requires you to choose for the least depth possible. And of course, it must be of standard. But it must be in the multiples of 50. Okay, so this preference here is actually a preference of construction method because it is actually a lot easier to fabricate concrete sections in multiples of 25 or even 50. Okay, so in this problem, we would now be making use of a compressive strength of 28 megapascal for the concrete and a yield strength of 420 megapascal for the rebars. So we will be making use of 16 mm DFB or deformed rebars for the design. And take note that the diameter of shear reinforcement or for the stirrups must be equal to 10 mm. Okay, so if you can remember the steps that we have enumerated previously, that for the typical steps, the first thing that we should do is for us to assume the trial section first. Okay, so suppose that in this sample here, it is indicated that the beam width is actually equal to 300 mm. So from that, guys, let us suppose that this is now 300 mm width. So for a moment, okay. So once again, for our beam width, it will now be this one here. So let's say that this is now our BW, 350 mm. Okay, so what about for the total depth? So according to the architect, you will be the one choosing, but of course, we would now be choosing for the least possible. So since it is not indicated here what the exact value of the depth is, we will now be referring to NSCP 2015 409.3 for the design limits, and according to table 409.3.1.1, this is now our minimum depths H given a support condition. So as you can see here, guys, that according to the problem, our beam is simply supported. So meaning, guys, by simply supported, we will now be making use of this equation here. So from that, this is now equal to the length divided by 16. Okay? So from that, guys, again, the H minimum that we will be making use must be equal to length divided by 16. So going back here, our length or the length of the beam that we will be designing is 6 meters long. And from that, substituting known values, that is 6 meters long. But it would be better, I think, if we would be converting that into millimeters. So 6,000 mm divided by 16. So take note that if you did not convert, take note that your answer is in terms of meters. Okay? But since I have converted, so this is now equal to, looking at the calculator, once again, so that is 6,000. Oops, sorry. 6,000 divided by 16. So that is now equal to 375 mm. Okay. So in a situation wherein you did not round, so 6 divided by 16. So take note that this answer here is in terms of meters. But since we have since we have converted into millimeters, that is now in terms of 375 mm. Okay, so before I proceed, take note, guys, that these factors here, or this equation here, can only be made use if Fy is equal to 420. And since in our problem, our Fy is equal to 420, so meaning that that is now our effective minimum H. Okay, however, if during the event that, let's say that your Fy is not equal to Fy, or your Fy is not equal to 420, it means that your answer here must be multiplied by this factor of 0.4 plus Fy over 700. Okay, so that is only for the event that your Fy is not 420. So suppose that your Fy is 280, substitute them in this equation, then multiply it by your solved H. Okay, but once again, since our value is 420, we do not need to make use of this formula. Okay, so according to NSCP, H min is equal to 375 mm. However, according to the preference of the architect, it must be in the multiples of 50. So from that, guys, since 375 is not in the multiples of 50, we would be rounding them up to 400. Okay, so with that being said, the total depth here is equal to 400 mm. Okay, so next up, since we already know our trial section, we would now be solving for the load, or we would now be estimating the loads. So if I am to draw the beam here, so let's suppose that this is now our beam. And of course, it is simply supported as seen above. So suppose that this is hinged. And let's say that this one here is a roller. And for its total length, that is now equal to 6 meters. So 6 meters. What is now the loads acting upon it? So we have here an unfactored superimposed dead load. So for our unfactored dead load, so let's suppose that this is now our unfactored dead load. So again, it is in terms of kilonewtons per meter. So this is now 10 kilonewtons per meter. Okay, so take note here, guys, that it is indicated here that this is superimposed. When we say superimposed, it means that it is on top of the beam. So in Filipino or in Tagalog, pag sinabi po natin superimposed, ang ibig sabihin po nun, yung load po na yan nakapatong po sa beam. Ibig sabihin, hindi pa po kasama yung beam dyan. Okay, once again, that is for superimposed dead load. So, is there any dead loads aside from the superimposed dead load that we should also take into consideration here? Of course, our beam here is actually subject to gravity. So actually everything here on Earth is subject to gravity, meaning that it also has its own weight. So from that, guys, we must also consider its self-weight. So I will be drawing them here. So for example, that this is now our self-weight. So of course, it is also a load. But what is now the self-weight? So for our computation for self-weight, so self-weight, that is basically equal to, so if we want our self-weight to be in terms of kilonewtons per meter, we must just multiply the unit weight of concrete times the cross-sectional area, and that is BW times D, since this is the cross-sectional area of our concrete. Okay, so in our loading here, substituting known values for, let's say, I will now be naming this as omega self-weight for the uniformly distributed load. This is now equal to, once again, the unit weight of concrete times B sub W times D. So for the unit weight of concrete, by default, we actually make use of 23.6 kilonewtons per cubic meter. In some reference books, they use 24 kilonewtons per cubic meter, but in my case, I will be making use of 23.6, which is the default value for board examinations. Okay, so that is once again 23.6 kilonewtons per cubic meter times BW, and according to the problem, that is 300 mm. So 300 mm times D, and the D that we have chosen for here is actually 400 mm. Oops. By the way, guys, take note that this is in terms of cubic meters. So meaning that, guys, that if you would be multiplying this, you must have unit consistency. So it is either you will be converting this cubic meter into millimeters, or better yet, if you would just be converting this in terms of meters. So from that, guys, this is now equal to 0.3 and 0.4. So from that is now equal to, so 23.6 times 0.3 times 0.4. So our answer here is 2.832. So 2.832 kilonewtons per meter. So from that, this is 2.832. Okay. So next up, this is now our dead loads. So we also have, of course, our live load. So it is now acting here. So this is now our live load, and that is 8 kilonewtons per meter. Okay, so there. Okay, so what is now the next step? So our next step here, so for a moment. Okay, so for our next step here is for us now to solve for the ultimate uniformly distributed load. So from that, guys, what I mean here is that for omega u, or say that for omega u here, this is equal to the factored loads. So factored loads. So meaning, guys, that for our factored loads for strength design, it may either be, since you only have dead loads and live loads, it may either be 1.4 DL or 1.2 dead load plus 1.6 live load. And we will be choosing for whatever is greater, or whichever factored loads is the greatest. So for the first one, for 1.4 dead load, so this now equal to, so for 1.4 dead load, that is this one's here. So this now equal to 1.4 times 10 plus 2.832. Okay? So looking at the calculator, so this now equal to, so 1.4 times, times 10 plus 2.832. So our answer here is equal to 17.9648. Okay, so let us check for the other possibility of 1.2 dead load plus 1.6 live load. So from that is 1.2 times 10 plus 2.832 plus 1.6 times 8. Okay, so looking at the calculator once again, that is 1.2 times 10 plus 2.832 plus 1.6 times 8. So our answer here is equal to 28.1984 kilonewtons per meter. Okay, so considering both of this, guys, of course, the greater one will govern. Thus, our beam would now be like this. So suppose that this is now our beam. So if this is our beam, and suppose that we have this as our support, and we have our roller here, the load combination that we will be making use is this one. So suppose that this is now our load. So here we go. Okay, so with that, guys, our omega u is now equal to 28.1984 kilonewtons per meter. Okay, so what is now the use of that WU? So that is now our basis for our required strength. So is it the case that our required strength is equal to 28.1984? So not yet. Since in USD, in beam design, we are referring to our ultimate strength or required strength as MU. So for MU, as you can see, it is moment. So from that, guys, in this one here, we would be solving for the moment or the maximum moment. So if I am to draw the shear moment, it would look like this. So it would look like this actually. So this is now the shear moment. So that is shear. And for the moment diagram, oh, by the way, that is not the shear moment, that is the shear diagram. And for the moment diagram, guys, it actually looks like this. So it is roughly like that. Apologies for this one here. It should be uniformly curved. So there. So the maximum moment for our concrete here is located at the midspan. That is for a simply supported one. Of course, if it is prop beam, it wouldn't be the case. Or suppose that it is cantilever beam, meaning that the beam has the maximum moment at the support. So once again, since in our problem here, we would only talk about simply supported beams, and from that, it is located at the middle part or at the midspan. That is for the positive maximum moment or positive MU. Okay? So how can we solve for MU? So it is either you would be basing it from your shear moment diagram, or if you want to memorize formulas, MU is actually equal to omega L squared divided by 8. So this is only for simply supported spans. Okay, so from that, substituting known values, our W is 28.1984 kilonewtons per meter times the length squared. So our length is 6 meters squared. So we would be dividing this by 8. So for the value of our MU, that is now equal to, so 28.1984 times 6 squared divided by 8. So our MU, or the MU that we will be using for our design, is positive 126.893 kilonewtons per, kilonewton meter. Okay, so take note guys that our moment here is positive. Meaning by positive guys, if this is now a positive moment, its bending would now emulate a smiling face. So meaning guys, if it is positive, meaning that its bending would now be like this. Okay? So this is now the manner of bending. And from that guys, as you can see, that the top portion would be the one that is subject to compression, and the bottom part will now be subject to tension. Meaning that for our design, okay, so for our design, the rebars should be located at the bottom part. Okay, since tension side is located at the bottom part. But for the event, for negative moment, okay, so for the event of a negative moment, so an example here is, for example, a cantilever beam. Okay, so suppose that we have a cantilever beam here, and if I am to draw its uniformly distributed load, it might look like this. Okay, so in the event of a cantilever beam, so if you would be drawing its moment diagram, it would now look like this. So this is now its moment diagram. And as you can see, that instead of having a positive moment, we now have a negative moment. And if it is a negative moment, as you can see guys, that for this particular sample, its manner of bending, since it is negative, emulates a sad face. Or it would now sag like this. So this is now its manner of bending. Okay? And just by looking at this figure, the one on top will be the one subjected with tensile forces or tensile stress, and the one at the bottom is for compression. So once again, this is for compression, and this is for tension. So since the tension side is at the top, meaning that in your design, we'll be designing it in such a way that the rebars must be on top. Okay? So, sir, how can I design this? It is basically a typical SRB. It is just that it is oriented 180 degrees. Okay? So, meaning guys, that for your compression block, it will now be located at the bottom part. And for the value of D, it would now be measured from the bottom part up until the center of your rebars. And this is now your value of A. So, all equations or all solutions that you have learned in the analysis of design is still effective. It will be that way. It is just that for your design, it is oriented in this manner. So, baliktad na po siya in Filipino. Okay? So, again, in our situation, it is a positive moment. Thus, our rebars will now be located at the bottom part. Okay, so proceeding, so let me just redraw our figure here. So if this is our figure, and then for our line, or for our breadth BW, that is now equal to 300. And for our depth, that is, of course, 400. Okay. So next up, what should we do now? So if we are now to look at our typical steps here, we have already finished all of this. So we already have our trial section. The load analysis, we have already done that. And for structural analysis for required strength, that is what we did seconds ago when you have solved for the maximum moment. For number 4, this is actually given already. Okay, so for number 5, we will now be solving for the required number of rebars. Okay, so for the required number of rebars, once again, we have these typical steps here. So I will first show you how to solve for it using method number 1. Then we will be resolving it using method number 2, I should say, and we will be comparing answers. And as for number 3, I think I will be leaving that to you since this is just direct substitution. Okay, so once again, I would just be comparing the answer in these two and prove to you that they are basically the same. Okay, so the next thing that we will be doing is for us, of course, to let me just once again redraw the section at this side in order for me to draw the stress diagram. So suppose that our rebars are now located at the bottom part. So I do not know how many rebars we need. So I will be assuming that it is only 4, but I think this is incorrect. So from that, guys, in our analysis, if this is now our stress diagram, if this is now our stress diagram, of course, the top part, so this top part here is now subject to compression, and thus this is now A. Okay, guys, so this is A. This still B sub W. Okay, and for this particular value, this is now our depth D. Okay, so this is now our depth D. Okay, so what is now the composition for our depth D? Or how can we solve for depth D? So suppose that we have this particular figure. Depth D once again is from the top up until the centroid of your tension members. Okay, so for our situation here, my first analysis is that I will be assuming that the rebars will now be just one layer. So meaning, guys, that this is now our D. So for the value of D, this is now equal to the total depth, which is the whole of this, minus the concrete cover, minus the diameter of the rebar, minus 1/2 of the diameter of the bar. Okay, so we already know the diameter of the bar and the diameter of the stirrups, but what about for the concrete cover? So for the concrete cover, it is indicated in the problem that, where is it? So it is indicated in the problem that it is a simply supported interior concrete beam. So looking at this table according to NSCP, that is table 420.6.1.3.1. So this is now our table for the specific concrete cover. And since in our sample here, our beam is interior, and if you would be reading the exposure, interior beams are not exposed to weather since it is inside. And from that, guys, for beams, columns, and pedestals, we will be making use of 40 mm. Okay, so from that, guys, our concrete cover is 40 mm. So in here, for our D, this is now equal to, so what is the value of H? So the value of H that we have used a while ago, that is 400 mm. So 400 mm minus the concrete cover of 40 mm minus the diameter of the stirrups of 10 mm minus half of the diameter of rebar that we will be making use, and that is 16 mm. So from that, solving for the value of our effective depth, that is 400 minus 40 minus 10 minus 16 over 2. So that is now equal to 342 mm. So again, that is now for value D. Okay, so let me just erase this in order for me to get more space. So I will just write that our D is 342 mm. Okay, so once again, in our situation here, this is now our compressive block. So this is now our compressive block or compression block, whereas this is equal to 0.85 F prime C, and this is of course A. Okay, so from that, the resultant of our compression block, or better yet, if I would not write the resultant here, but this is of course A. And for D, or for the stress of steel, this is now equal to AS FS. But since we are designing, it is better to assume, and according to the code, our steel must yield. Okay? So again, in designing, always assume that Fs is equal to Fy, because compression controlled is not allowable according to the code. Okay, so that is now ASFY. So for the first one here, for our first method, we would be solving for A by summation forces horizontal. Okay, so from that, guys, so summation forces horizontal is equal to 0, whereas compression is equal to tension. So from that, guys, 0.85. So the resultant of this block here, so that is 0.85. F prime C, A, B sub W is equal to ASFY. Okay, so ASFY. However, if you are to look at this equation, we already know the value of F prime C, we already know the value of B sub W, and we also know the value of Fy already. However, we do not know the value of A, and we still do not know the value of AS since we are designing. Okay, so from that, we cannot make use of this equation right away. Instead, we must use for another equation. And that other equation is, of course, the summation of moments, or PMN. Okay? So that is for PMN. Since PMN or MN is equal to 0.85 F prime C A B sub W times D minus A over 2, we can now say that phi mn is equal to 0.9. So once again, I will be making use of 0.9 because I will assume that my section is tension controlled. Okay, so that is 0.9. So this is now the value of phi times 0.85 times F prime C times A times B sub W times D minus A over 2. Okay, so if you can remember that for our VMN, it must be greater than or equal to the value of our, where is that? The value of mu. So from that, for our lower limit, we can assume that VMN is equal to mu. Okay? So from that, what is once again the value for our mu? So according to our solution a while ago, mu is equal to, so where was that again? So mu that we have solved for is 126.893. Okay, so I would just box this. So mu is equal to 126.893, but take note that this is in terms of kilonewtons per meter. I mean kilonewton meter, I should say. Okay, so from that, guys, so VMN, this is mu, and from that, 126.893 is equal to 0.9 times 0.85 times F prime C A B sub W times D minus A over 2. Okay, so in this equation, guys, we only have A and A unknown. So from that, we will now be solving for A. Okay, so take note, guys, that in our mu is in terms of kilonewton meter. So the first thing that we should do is for us to convert this first into Newton millimeter, because our answers here, or in our situation here, this is in terms of megapascal. This is in terms of millimeters. This is also in terms of millimeters. And with that, guys, our answer must be in terms of Newton millimeter. So if you would be converting kilonewton meter into Newton millimeter, just multiply this by 1 million. Okay? So that is now our conversion factor. Okay, so substituting all known values, so 126.893 times 10 raised to 6, that is now equal to 0.9 times 0.85 times f prime c of 28 times a, we do not actually know what the value of a is, times bw, and our bw is 300 mm, times d, once again, the value of d that we will be making use is 342, minus a over 2, and a is also unknown, so a over 2. So you can make use of shift solve here, however, so we would encountering some problems. So first problem is that we might encounter lengthy calculator solution, so it might take a while. So another thing, as you can see, that this will result to a quadratic equation, meaning that we have two possible answers. So meaning that if you would be using shift solve, the wrong answer might be the one being displayed. So with that, guys, I will not take any chances. Rather, I will be making use of mode 5.3 or the quadratic equation mode. Okay, so what I will do is that I will be orienting, or I will be rearranging our equation here in such a way that it will now look like this: ax squared plus bx plus c is equal to 0. Okay, so first I will be once again simplifying this equation. So this is now equal to 126.893 times 10 raised to 6. This is now equal to, so if I am to multiply all of this, that is 0.9 times 0.85 times 28 times 300. So that is now equal to 6426A. But if I want to multiply that by 342, so I will now just be multiplying this by 342. So that is now equal to 2197692A. Okay, so what about for this one here? If I am now to multiply this equation or this side to a over 2, so this is now equal to minus. So going back to our answer here, 0.9 times 0.85 times 28 times 300, we would just be dividing this by 2. So our answer here is 3213A squared. So rearranging this is now to become 3213A squared minus 2197692A plus 126.893 times 10 raised to 6. This is now equal to 0. Okay, so from that, guys, I will now be typing them to our calculator. So I will now go to mode 5.3. So once again, I will be assuming that this is A, this is B, and this is C. Okay, so from that, looking at the calculator to your left, 3213, negative 2197692, positive 126.893 times 10 raised to 6. Okay, so with that, guys, we have two possible answers. So the first answer, so for A1, that is now equal to 620.335 mm. And for A2, so another possible answer is 63.665 mm. Okay, so which one of this is the correct one? As you can see, guys, that in our depth is 342 mm, meaning that a compressive block of 620 is actually impossible. So from that, guys, we will now cross this out. And thus, the value of A that we will be using is 63.665. Okay, so from that, guys, if that is now 63.665, we can now substitute it to this equation in order for us to solve for the value of AS. So going back to summation of forces horizontal, whereas C is equal to T. So this is now equal to 0.85 times F prime C times E times B sub W is equal to AS Fy. So substituting all known values, 0.85 F prime C. So 0.85 F prime C, and F prime C is equal to 28. And for the value of A, that is now equal to 63.665. As you can see, that is what we have solved for earlier, times BW of 300. So this is now equal to AS times FY of 420. Okay, so was it really 420? So is it 420? Yes, it is 420. Okay, anyway, so with that, guys, solving for AS, this is now equal to. So by the way, this AS here is now our AS required. So this is now equal to, so going back to my calculator mode or computer mode. So that is now 0.85 times 28 times 63.665 times 300 divided by 420. So this is now equal to 1082.305 millimeter squared. Okay, so this is now our AS required. Okay, so if I am to go to our limits, okay, so in this slide here, I will now be writing our limits. Okay, so for our limits, on the left side will be our lower limit, which is for rho min, and on the right will be our rho max. Okay, so for our rho min, according to NSCP, so rho min is equal to 1.4 over Fy, and rho min is also equal to square root of F prime C over Fy, whichever is larger. Okay, so just because that it is included minimum here doesn't mean that we will be making use of the minimum value between the two. So that might sound confusing, but take it this way. So I think it would be better if we would be substituting it first and solving for the values. So for 1.4 over Fy, that is 1.4 over Fy of 420. So this is now equal to, so looking at the calculator to your left, 1.4 over Fy of 420. 420. So that is now equal to 0.0033. Okay, so square root of F prime C over Fy, this is now equal to, so F prime C is equal to 28. So by the way, we have another, this is incomplete. This must be for Fy. So square root of F prime C over 4 Fy. So 4 times Fy of 420. So in here, this is now equal to the square root of 28 divided by 4 divided by 420. So our answer here is 0.0031. Okay, so we will be choosing the larger value, but why is that the case? Because if we would be choosing the lower value, what if for suppose that your raw actual is equal to 0.0032, okay? So if it is 0.0032, it means that it is within our raw minimum here. But if we are to consider this, it has already failed because it is now below minimum. So from that, guys, we will be choosing for the larger value. Or if you do not choose between the two, then always display the two. That is 0.0033 and 0.0031, and always check. Okay, so for example, if let's say the raw actual is 0.0004, so is it greater than 0.0033? Yes, of course. Is it greater than 0.0031? Yes, of course. Then meaning that the raw of 0.004 is within raw minimum. Okay, so for our general equation here, or general rule, that the raw actual must be less than or equal to raw max. But of course, it must be greater than or equal to raw min. Once again, in the situation wherein raw actual is less than raw min, meaning that choose raw min. But if raw actual is greater than raw max, meaning that you cannot choose for raw max any longer. Instead, you must design or redesign. So by redesigning, it is either you change the beam dimensions or just design it using doubly reinforced beams. So that is a video to be followed. To follow. Okay. So that is now for rho mean. So I would just be erasing this other one since 0.0033 would be governed. Okay. So from that, guys, I can now say that my minimum area is now equal to, so once again, that is rho mean times BWD. So from that, this is now equal to 0.0033 times what is now our BW. So BW is 300 and depth is 342. Was that 342? So our depth is depth is 342. Okay. So our AS mean is now equal to 0.0033 times 300 times 342. Okay, so our answer here is 338.58 millimeters squared. So this is now the minimum area required. Then for rho max. So again, for rho max, we actually have two to choose from. So it is either you will be choosing rho max here or rho max here. But then again, I would rather choose the third equation here in order for me to ensure that it is really tension controlled, since I have used a value of V is equal to 0.9. If this is your rho max or the rho max that you will be choosing, you will still solve for the value of V. Okay, so once again, I will be making use of this as our rho max. And besides, if we would be making use of this as our rho max, it is still within the code. Okay, so for that, for my rho max, this is now equal to 0.85 times f prime c divided by fy times beta 1 times 3/8. Okay, so from that is now 0.85 times f c prime of 28 divided by 420 times what is our betas of 1. Since our fc prime is 28, meaning that beta 1 is 0.85. So times 3/8. So meaning that for my rho max, that is now equal to, so that is 0.85 times 28 divided by 420 times 0.85 times 3/8. So our rho max here is now equal to 0.018. Okay, so from that, our AS max, so just multiply rho max by BWD. So this is now equal to 0.018 times 300 times 342. So from that, guys, 0.018 times 300 times 342. So our answer here is now equal to 1846.8 millimeter squared. Okay, so going back to our limit, our AS required is 1082.305. And as you can see here, that it is greater than the minimum. So AS required. So it is greater than AS minimum. And it is also greater than, it is now less than our max. So this is now AS max. So from that, guys, this is now our basis for our design. So again, this is now our AS required. Okay, so since we are solving for the number of rebars, so the number of rebars, and the number of 16 mm rebars is now equal to AS required divided by the area of one rebar. So that is pi over 4 times the diameter of bar squared. So from that, this is now equal to, so 1082.305 divided by pi over 4 times 16 squared. Okay, so from that, this is now equal to 1082.305 divided by pi over 4 times 16 squared. So we now have 5.3829 pieces. But since we cannot buy 0.3829 pieces, we must round this up to 6. So for the number of 16 bars, that is equal to 6 pieces required. Okay, so our next step here is for us guys to check for the spacing. So again, we would now check the spacing of the rebars, but take note guys that of course it must be greater than this spacing. However, before I check for the spacing, in the next video I would first prove to you these values here. So again, what we did was that we have solved for our value or our AS required using number 1. So I will first solve via number 2. I will solve for the AS required using this equation. Then I will now check for the spacing requirements. So that is in the next video. So there.